Let's talk about exponential functions. An exponential function is a function in which your argument of your function is in the exponent of your function. So that is to say something like y is equal to 2 to the power of x, where what we're plugging into our function here is in the exponent of our function. Um, Something like y is equal to x squared, this would not be an exponential function because we see here that what we're plugging in is actually the base of our function. So now that we know what an exponential function is, let's identify a couple of key features of them. First off, what we call here, whatever we're raising to the power, we call this our base here. And that base must be greater than 0. And the reason why that base must be greater than 0 is essentially we're saying we can't raise a negative number to a power. So for example, if I had, for example, negative 2 raised to the power of x, just pause and think about this for a moment. As x increases, the outputs of this function are going to oscillate back and forth between positive and negative values that actually increase in absolute value. You would get when x is equal to 1, negative 2. When x is equal to 2, you get a positive 4, then negative 8, positive 16, and so on. So that's not how an exponential function behaves. Our base also cannot be equal to 0 or 1, because if your base were equal to 0 or 1, you would actually have a constant function. 0 raised to any power is always going to be 0, and 1 raised to any power is also going to be 1. So those are the conditions for the base. Now, as for what the conditions for what we can plug into our function or our domain, we would say that x can be all real numbers, or we can write this in interval notation from negative infinity to infinity. So you're actually allowed to plug in any number that you want for an exponential function, provided that your base is non-negative and not 0 or 1. Now, with that said, let's actually look at some parent functions here. So let's go ahead and look at the graph for 2 to the power of x. So for 2 to the power of x, let's just go ahead and plot these values here. And if we take 2 and raise it to the negative 2 power, this would be equivalent to 1 over 2 squared, which is just 1 over 4. 2 raised to the negative 1 power is going to be 1 over 2. 2 raised to the 0 power is 1. This would give us 2, and this would give us 4. So if I plot those points, negative 2 gives us 1/4, negative 1 gives us 1/2, 0, 1, 1, 2, 2 to the 4. This function would look something like this. Okay. Now notice here that our function will actually never cross the x-axis because no matter how negative x gets, so as x approaches negative infinity, there's still no x value that we could ever plug in that would ever cause this function to be equal to 0. So we see here that it's going to hug the x-axis, but it will never actually touch it. And for that reason, we have a horizontal asymptote of y is equal to 0. Okay. Now, let's go ahead and let's try looking at this function now. Go ahead and take a look at 1/2 raised to the power of x. Now, for 1/2 raised to the power of x, we'll notice here, well, maybe actually let me ask that. Is there any way that I can leverage what I just did with 2 to the power of x to graph 1/2 to the power of x? Perhaps another way of asking that is there any way that I could rewrite 1/2 to the power of x in terms of what I have just graphed here of 2 to the x? And hopefully what you saw is that, yeah, I could actually rewrite 1/2 because 1/2 is equivalent to 2 to the negative 1 power. So if I raise that to the x, this is equivalent to saying 2 to the negative x. So if that's the case, that's simply a reflection over the y-axis of what we initially graphed. That is to say, I could just take all my x values here and flip the signs. So 2, 1, 0, negative 1, negative 2, which would then give me 1/4. My y values remain exactly the same. So if I graph this, 2 gives me 1/4, 1 gives me 1/2, 0, 1, negative 1, 2, negative 2, 4, and this graph is hit the Siri button there. Sorry about that. Okay. All right. So we're still going to have a horizontal asymptote of y equals 0, but we can clearly see that this parent function now is a reflection of what we initially graphed here. Now, I'm highlighting these to show you, one, a transformation, but also to indicate an example of what we call exponential growth versus exponential decay. Well, when do we have exponential growth? Well, exponential growth occurs when your base is greater than 1, and exponential decay, when the outputs of the function are seemingly plummeting in value, occurs when your b value is between 0 and 1. Okay, so it's really all about that base, not to necessarily just try to quote that song, but it's all about that base. When that base is greater than 1, we're going to see exponential growth. When b is a value between 0 and 1, we're going to experience exponential decay. And again, just to hammer a few more things home, we can see that both of these functions have a horizontal asymptote of y equals 0. The domain of both of these functions, we said that what we can plug into our function will be all real numbers. Whereas we can see here that our range right now currently is 0 to infinity. Only positive values can come out of this parent function. Now, vertical shifts or translations up and down can clearly change the range here. So that's a good kind of segue into talking about transformations. So let's talk about transformations here. Most of the transformations that we've already discussed previously in this course are going to apply here with exponential functions. So we can still see things like vertical stretches or shrinks with an a value. And we can also see things like horizontal shifts, both left and right, as well as vertical shifts. Okay. So let's go ahead and quickly graph these transformations. Take a look at this first function here. What do we notice? We have a horizontal shift to the left 2 units. Okay, we know that when we're adding to our argument, we're actually shifting to the left 2 units. Well, if I go back actually, and I copy and paste these values, let me actually just clean this up real quick. Just go 1/4, 1/2. Because I'm going to just copy and paste these because I'm going to use these again. So let's copy that. And if I take these same values, well, let's think about this for a second. X plus 2, if I take my argument and I set it equal to where my x value was originally, which was at -2, and I isolate x, I see that x now is equal to -4. So that -2 goes to -4. And that way we can see why it's a horizontal shift to the left 2 units. So that -2 goes to -4. If we continue to shift left, this -1 goes to -3. This goes to -2. This goes to -1. And this goes to 0. So what does this graph look like? Well, let me actually do this graph here in green. So -4 gives us 1/4. -3 gives us 1/2. -2 gives us 1. -1 gives us 2. 0 gives us 4. And so this graph is going to look something like this. And if I just take this graph here that I initially graphed here, let me just take this. And I plot it on the same axes so we can kind of see them side by side. Oops, there we go. Now it's in the right spot. So we can clearly see that horizontal shift to the left 2 units. Okay. So what do we notice about the y-intercept now? Well, now the y-intercept has shifted to 0, 4. Okay. Because of the horizontal shift to the left. Our domain is still going to be all real numbers, but our range now is going to be values from 0 to infinity. Okay. Go ahead and pause the video right now and try to do this next problem here. 2 to the x minus 3. Well, I'm going to go ahead and I'm going to plot the original function here. You don't always have to do this, but I'm going to do this just because I want to clearly identify the transformations and compare them. So here are the original values for my function. Hopefully we can clearly see that this is a vertical shift down 3 units, down 3 units. And what that means is I'm going to take all my y values and I'm going to subtract 3 from them. So 1/4 then goes to -2 and 3/4. 1/2, let me actually zoom in here. -1/2 goes to -2, 1/2. Let me make that negative. 1 minus 3 is -2. 2 minus 3 is going to be -1. 4 minus 3, excuse me, is going to give us +1. So if I graph these points, -2 giving us -2 and 3/4. 0 gives us -2, 1 gives us -1, 2 gives us 1. Something like this, we would see can be graphed pretty easily. Oops, don't want to. Okay, and that gives us a pretty good sense of what that vertical shift down 3 would look like and how that would impact our graph. Okay, so our y-intercept would then be, again, 0, -2. Our domain is still all real numbers. That hasn't changed, but now what has? Now that we have a vertical shift down 3, our range now changes down to -3 to positive infinity. So when we're doing these transformations, to kind of really summarize the main thing that I'm emphasizing is identify whether or not your transformation is horizontal. If it is a horizontal transformation, set your argument, what I've just highlighted here, set your argument equal to where the x value was originally and solve for x. That'll take care of all of our horizontal transformations. If it is a vertical transformation, in this case something like -3, just directly apply that operation to your y values. And if you do this with your original parent function values, this becomes actually pretty straightforward to graph. So I'm going to allow you to go ahead and pause the video and try these on your own time. But I actually want to jump and do these next two problems together. So let's just quickly do this. So if I take my original x and y values, I'm going to place them here. Let's go ahead and try to identify the transformations in this problem. So first off, we see that we have a reflection over the y-axis because there's a negative being multiplied by the x. We're going to horizontally shift to the right 2 units now. Why are we shifting to the right 2 units? Because of that reflection, which reverses the order of our shift. We have a vertical shrink by 1/2, and we have a vertical shift down 4. Okay? So if I were to take this argument, kind of what I was mentioning earlier, if I take that argument and I set it equal to where my x value was originally, so negative x then is equal to -4, x then is equal to +4. Think again about what I just did. I shifted to the left 2 units, then reflected it over the y-axis. So if you wanted to change the way you wrote this, we could say horizontal shift to the left 2, reflected over the y. So that x now becomes +4. So shift it to the left 2, so that -1 becomes -3. Shift over, that -1 becomes +3 after we reflected. So 0, shift to the left 2, that's -2, reflected over the y-axis, +2. So you can see kind of where this is going. 1 goes to -1, but we reflect it back to its original spot. 2 goes to 0, and it reflects onto itself. So those are our horizontal transformations. What about our vertical transformations? Let me just do this in a different color. Our vertical transformations, we're going to multiply by 1/2. We're going to vertically shrink it by 1/2, and then we're going to subtract 4 from it. So 1/4 times 1/2 is 1/8 minus 4. That's -3 7/8. Okay. 1/2 times 1/2 is 1/4 minus 4, -3 3/4. 1/2 times 1 is 1/2 minus 4 is -3 1/2. You can see where this is going. 2 times 1/2 is 1 minus 4 is -3. 4 times 1/2 is 2 minus 4 is -2. So now I think I'm ready to graph this. 4 yields -3 7/8. 3 gives us -3 3/4. 2 gives us -3 1/2. 1 gives us -3. 0 gives us -2. So this graph is going to look something like this. Okay? And our horizontal asymptote was initially at y is equal to 4, but because of our vertical shift down 4, we're now at y equals -4. Our y-intercept we found was 0, -2, and if that doesn't come up naturally through our table of values, you can always plug 0 into your function. Again, we're noticing that our domain does not change. And our range, in this case, because we vertically shifted our function down 4 units, now goes to -4 to infinity. Finally, what are we noticing about this function over here? Well, it's probably worthwhile over here on the right side to make sure that we understand what E is. E is what's known as the natural number, also known as Euler's number. and its approximate value is 2.7182818. Well, where does this come from? This comes from taking this expression and raising it to the nth power. And as n approaches infinity, that is to say, as n gets very, very, very large, then this output is going to approach this value. And e is probably one of the most famous irrational numbers out there next to pi. I mean, those are the two big hitters in terms of popularity and also their importance in mathematics. So you're going to see e pop up pretty naturally, pardon the pun, a number of times when we try to calculate things with things like compound interest or model functions that grow exponentially. We don't have to worry about that too much right now, but we should basically understand what the function of e looks like. So we can say the following. We can say that the e function would look like as such. When x is equal to 0, e to the 0 power is going to be equal to 1. When x is equal to 1, oops, sorry about that. When x is equal to 1, e to the 1 power is just e. So this function is actually really easy to graph. When x is equal to 0, y is equal to 1. When x is equal to 1, y is equal to e, which is about 2.718. So this function is going to look something like this. So we see that exponential growth. It's still going to have a horizontal asymptote of y equals 0. And in fact, this function behaves a lot like y equals 3 to the x. Not quite as dramatic as a growth. Our y-intercept is still 0, 1. And our domain is still going to be negative infinity to infinity. And our range is still going to have to consist of just positive numbers, unless we have some type of vertical shift. Okay? So hopefully this video has been helpful in kind of introducing what exponential functions are, how they are graphed, and how we can apply the same